Hi guys. Okay, so let's look at this chapter on solutions. So today we are going to cover, first of all, what are the solutions, the different types of solutions, then the formation of solutions, which is the, how are the solutions formed, the concept of saturated solutions and the unsaturated solutions and the supersaturated solutions, and then the hydration or the solvation of ions in the case of ionic compounds, and the like dissolves like concept in the case of covalent compounds. Then we're going to look at the electrolytes, the strong, weak, and the non-electrolytes, then the solubility rules, okay, and then the effects of the temperature and the pressure on the, on the different types of solutions. And also with the solubility rules, we are going to look at the ionic, net ionic, and the this is the net ionic and the net ionic equations. And then also we're going to look at the spectator ions. Okay. Now, let's first, and once again, sorry, this is a daytime, and anytime I'm doing these recordings during the daytime, there is a general disturbance outside. So we have some constructions happening and some people come to do the cleaning and so forth. So from intermittently, there's going to be some disturbance. So please bear with me. All right, so here we have the concept of, first of all, what are solutions? What is the term solution? Okay, so the solutions are those, basically they're mixtures. Okay, so this is a physical change and it's a formation of mixtures. Okay, so this is basically leads to the formation of mixtures, and these mixtures are basically homogeneous mixtures. Okay, mostly homogeneous. Homogeneous means they all look the same. Okay, next is that this is not a permanent change. When we say this is a physical change, means that it is not a permanent change. So when we say it's not a permanent, that means no new substance is formed. No new substance is formed. So even though they may look like it's a homogeneous mixture, but no new substance is formed. So this means that you can separate the individual, components by physical means. So separation of individual components is possible. Okay, now, okay, separation of individual components. Sorry about that, components. All right, so this is a very basic thing about what is a mixture, or like what is a solution. But solutions are made up of two main components. One is the solute, S-O-L-U-T-E, and the other is a solvent. Okay, solvent. Now, when the solute mixes with solvent, then a solution is formed. Then only a solution is formed. So you see that solute has less, it has got less letters. So it is a small, that's how I remember it, that solute is smaller in amount and solvent is bigger in amount. So we have here, this guy's solute is always going to be the smaller amount, and solvent is in larger amount. Okay, and then they form a solution together. Okay, now let's look at this for examples. Some example here is that of sodium chloride. So sodium chloride is a solid. Okay, that is a table salt. When you mix it with water, H2O, which is a liquid, okay, you now pay attention to the states also. Then it gives you sodium chloride, okay, and that is aqueous, means it is soluble in water. So soluble in water, it dissolves in water and it forms a clear solution. It depends, if you have a little bit amount of it, it is formed a clear. So when it is clear solution, it looks clear. So that means it's all nice, clear, one clear, like a solution, then it's soluble in water. Okay, then that's sodium chloride. Now, like I said, you pay attention to the states, solid, and this is a liquid. When this mixes together, this aqueous stands for solubility in water. When it's a clear, looks clear. Okay, so that's a very general introduction. So that's part, this is the, let me just label this as part 1. Okay, next we are going to look at types of solutions. Types of solutions. Now, generally we look at the, so let's put this here, solute, and let's put this here, solvent. So generally we look at like sodium chloride or maybe, you know, sugar or things that dissolve in water. Okay, so here we have when a solute is a solid, okay, solid, and the solvent is a liquid. So in this case, what kind of solutions do you see? You will see in a solid, when it's a solid and the other one is a liquid, then it's like sodium chloride, NaCl, or sugar. Okay, sugar is also a solid. So solid and solid mixing in water. Okay, water is a liquid. So then in that case, that solution that is formed looks nice and clear. Okay, clear solution. Next is, you can also form a solution by dissolving a liquid, small amount of liquid in a large amount of liquid. A small amount of liquid is, for example, small amount of liquid is, for example, you can say alcohol, little bit of alcohol in large amount of water. So generally, you know, solutions, you need a solvent. So water is like a universal solvent. So next is alcohol in water, or you can also say like a little bit of orange juice in water, right? Orange juice or apple juice, you know, apple or lime or whatever, you know, juice in water. So that is also, so a little bit of one thing in a large amount of something will make a solution. Next is, if you have a gas bubbled in a liquid. So gas is, for example, you see carbon dioxide is bubbled in most of the waters. So carbon dioxide is a gas. Here, alcohol is a gas. This is a liquid. This is a liquid. This is also a liquid. Okay. Now, carbon dioxide as a gas bubbled in water as a liquid, and that gives you a soda. That gives you a soda, you know, soda. So liquid, okay, that gives you soda water. Then otherwise, you know, nitrogen gas is also bubbled in like a solution of coffee, and coffee is a liquid, you know, so that nitro brew or whatever. Okay, so that's one type of solutions commonly we know. Other types are, for example, a small amount of solid dissolved in a large amount of solid. A small amount of solid, like for example, you have carbon, little bit of carbon on a large amount of carbon, a large amount of iron. Okay, so that gives you steel. Okay, little bit of copper in large amount of gold will give you, like, or silver or gold will give you you know, that jewelry, gold jewelry. If you want to hold, because gold is very soft, gold melts like it flows. So in order to hold the shape of a jewelry, you need to add a little bit of copper, little bit. Okay, so that's one thing. For example, small amount of zinc put in a large amount of copper, that's going to give you brass. And you've seen like brass, you know, like this, statues and those things. So that's like, you know, very basic thing. And then there's amalgam. I think it is zinc in mercury, you know, that gives you that thing for the filling of the teeth. All right. Next is, for example, you have little bit of liquid dissolved in large amount of solid. For example, you have water here, okay, dissolved water as a liquid. So this is a solid, this is solid, this is solid, this is also a solid, solid. Okay. Now, large amount of solid, for example, flour, and that gives you a dough, right? So in other words is, for example, you have a gas, little bit of gas dissolved in large amount of gas. So for example, large amount of gas is, let us say, air, and little bit of air, a little bit of gas is like smoke. Okay, smoke in large amount of air. So smoke, S-M-O-K-E, smoke is a gas and air is a gas. All right. So another thing would be like a liquid in a gas. Like for example, liquid is like water droplets. You know, so water droplets are like for example, you know, fog or mist in air. So that is also a solution. Mist is like liquid droplets, right? And air is a gas. So that creates that, you know, so that is a solution, okay? So these are the different types of solutions that we know of. Next is, we are going to look at the formation of solutions, third part. Now the third part is, how are the solutions formed? So formation of solutions. So let's look at the formation of solutions. First, we are going to look at a very general concept about how they work. General, first is general, like a general way of, you know, and then we're going to look at the ionic, and then we're going to look at the covalent. So let's look at first the general formation of solutions. So how do the solutions form? So here's the thing. Okay, keep this in mind that these are basically electron clouds, you know, atoms, molecules, they are basically electron clouds. So they're like, you know, clouds just by themselves, you know, like this, they are arranged. So like I said, they're clouds, they're circular. Or even if they are long, it doesn't matter. Even if they are long clouds, it doesn't matter. Whatever their shape is, it doesn't matter. But what is important is, if you look at it, that they have like all these empty spaces in between them, right? These empty spaces are the spaces that, you know, which are called the intermolecular spaces. So these intra is in between these, not, one second, intermolecular, and intra is inside, intermolecular spaces, yeah, intermolecular spaces. So here is the intermolecular space. It's an empty space. It's an empty space. Okay, so this is the solvent with the intermolecular spaces in between these particles, in between the molecules of the solvent. So let's do this. This is the solvent molecule. This is a solvent molecule. This one is another one, another one, another one. So all these are like clouds. And yeah, they're soft, they're mobile, they move, you know, they take the shapes of the container. Even with that, they will always have this space, empty space. So this is the empty space. And because of this empty space, they are mobile, they move, you know, empty space. Now, when you add a solvent, now you are adding a, so this is the, when you add a solute. So here comes a solute, and these solute particles are, you know, small amounts. And it could be anything, you know, if you're talking at water, then you're looking at like, you know, sodium chloride, or you're looking at potassium chloride, potassium nitrate, sodium nitrate, you know, any of these ionic compounds. Or you can also look at some of the ones that dissolve in water, like sugar. You can also look at like a liquid part, like you can look at methanol, you know, alcohol, all these pieces. So what happens is they come and they begin to occupy the empty spaces. They occupy the empty space. So when they come and sit in the empty space, so that is when they form the solution. So ordinary in general, what is solution formation? When solution generally, unsaturated. Unsaturated means when there is still empty space available. So unsaturated solution is where you have plenty of space is available, plenty of empty space available. Empty space is still present. I don't know if you would get that, is present. Okay, so in that case, the solute occupies empty space. But plenty of empty space is still present. Okay, next is the saturated solution. What is a saturated solution? Saturated solution means when all of the, let me just draw also, saturated solution. One second. So how does this look like, the first one? Empty. Okay, so here, let us say you have a container or a cup or a glass, okay? And here you put some water. Let's say water is right here. You put some water here and it's nice and clear. You cannot see, the solute particles. You cannot see. So solute particles occupy the empty space, but solute particles not seen. Solute particles are invisible. So solute particles are invisible. Solute particles are invisible. That means the solution looks clear. Clear solution. So here I will say solute particles and looks clear. So light can pass through. Okay, so that is the unsaturated solution. Saturated solution, in that all of the empty space is occupied. Okay. Solute particles may be solute particles. It depends, what it is. Some solute particles may be visible. You might be able to see them. How? You might be able to see them like the solution may start to look like milky, like turbid. Okay, so it may look, depends, what you're mixing, may look turbid, T-U-R-B-I-D. Turbid means like milky. Okay, you might be able to see the particles. So in this case, here is your tumbler, and in that tumbler, you will have, here is your tumbler, and in that tumbler, you have the particle, the solution is here, but in the, the solute particles may be seen, so like that. You may be seen, but they are not like, it's like more like, it's like a milky, more soluble, more like, so it looks like something is there. Okay, so same thing here, you will see that the increase in the solute particles are going to occupy a lot of space here. So you won't be able to, like, no more empty space. Okay, now next is the supersaturated solution. Supersaturated. Now, when we say supersaturated, means that like not a single spot is available. So where are the solute particles going to go? Well, they have to settle down. So supersaturated solution, and that is when all of the empty space filled up. Okay. Not a single spot is left. You may try to shake. Here you may try to shake and make some space in the second case, in the saturated case. But in supersaturated, no, not a single spot left. Okay, so in that case, what will you do? The solute particles settle down at the bottom. Solute particles settle at the bottom. And you can clearly see them settle at the bottom. Settle at the bottom. Okay. And here you can clearly see, you know, this is how the solution looks like. So you may see a clear solution on the top, but the solid, the saturated, the solvent, the solvent containing the solute, nice and clear on the top. But here is your solute sitting at the bottom. So here you will see after some time, you may try to shake it, it will try to mix, but in the end, the solute settled at the base of the, you know, containers. So, and then here you will see a clear solution. And that clear solution contains the right amount of solute plus the right amount of solvent. Okay, that amount. So that's the one. So that is how the supersaturated looks like. So we looked at these three types of solutions. One is the unsaturated, where there's plenty of empty space available and you can add more of the solute there. It looks like a clear solution. Then comes a saturated solution where you can make out like, okay, this has maxed out. You may see some turbidity. You know, turbidity means when it's not clear. So let me put this here. When this is, may look turbid, milky, and not clear. Not clear. And so here in the next is the supersaturated, in which the solute particles settle at the bottom, but a clear solution on top. Okay, so because it settles in the weight, you know, so these are the three types. Now, here is another very general analogy you can see is akin to a bus. Okay, so here is the school bus. So like here, this, just take this analogy or analogy to a school bus. Okay, so here is your bus or school bus or any, you know, not even a school bus. Let's just do it to a bus, just a regular passenger bus. Okay. Okay, so here we have this bus, which is the last bus of the day. Okay, and this bus is carrying these passengers. So initially, this bus is like just, you know, empty, like vacant, and it comes and stands at the stop. So at the stop, the bus stop and the stop sign or bus stop, at the bus stop, there are people standing, waiting to board the bus. Okay, and it's a completely empty bus. Okay, so it's a completely empty bus. All right, now what we see here is that these are the people standing, wanting to board the bus. So when the bus comes at the bus stand, they board the bus. So when they get in the bus, they take the empty seats. So first is obviously they take the seats are empty. So they sit on the seats wherever they want. Okay. So the first is all the empty seats get occupied. All right. Next is the bus begins to move, goes to the next bus stand. More people are standing there. They take care, they board the bus. Next is let's say they're occupying some of the empty seats, remaining empty seats. So second is they take care of the remaining, they sit down on the remaining empty seats. Next is the bus moves again. And now the bus is moving, and when it moves, goes to the next bus stop, nobody gets out of the bus, and the people are still waiting at the next third bus stand, waiting to board the bus. Then when they see nobody's getting out, all the seats are occupied, where are they going to stand? They take the aisle. Okay, they stand in the aisle, basically. They're standing. So you see that? Some people may try to move around, may try to, give space to seniors or some pregnant people, or maybe giving space to, the disabled people. Some people may try to move their kids on their seat. Some people may try to move, little bit adjustments, So little bit remaining seats there were, and some adjustments here. The people, once you come in the aisles, there is some adjustments happen. So this is a situation where they're trying to adjust, is like it is getting saturated. Okay, so when the people are standing in the aisle, you can see the people standing in the aisle. You can see them. You can see people standing. Okay, from the distance you can see. So these first two cases are the saturated solution. The first two are saturated solutions. And the second one is, oh, sorry, not the saturated. This is the unsaturated solution. Unsaturated. This is unsaturated, where there's some space still there. Unsaturated solution. Okay, so now from now onwards, for the solution, instead of writing this big thing, I'm going to write down SOL raised to the power N. Okay, I'll do that. And then for the concentration also, concentration is the amount. So concentration, I'm going to write down either like concentration is the amount of solute in the solution. Okay, so either it is represented as a square bracket, or I'll write down here concentration raised to the power N. So just the short forms. All right, so here we have this. The first one was the unsaturated. Then the next one, after some adjustments, all the space gets occupied, people standing in the aisle, no more space left, then it becomes a saturated solution. Okay, so this is how you would see them. Next is the last one, where there is no space available and people are still standing in the bus, people are sitting in the bus, nobody is able to move also, right? Even if there's some adjustment is done, what happens? There are still people standing at the bus stand, wanting to board the bus, wanting to go home. That's the last bus of the day. So what are they going to go? They are going to sit on top of the bus. Okay, so when they sit on top of the bus, they have no other, and this happens, this happens in those countries where there are limited resources. So the people on top, sitting on top of the bus. So we can see from a distance, people sitting on top of the bus. We can see from a distance, people standing in the windows, right? People standing in the windows. Here, we can see them. So that means this is a super saturated solution. Okay. So this is the look of these are the looks of these, the bus with the people. All right. Now we have, next part is the formation, saturate. Now we are going to look at hydration, another concept here. So formation of the solution, first is the general. Okay, next part is the formation of solutions in the ionic compounds. Formation of solutions in ionic compounds. Okay, now ionic compounds. Ionic compounds are made up of metals and non-metals. So whenever metal combines with a non-metal, or a metal combines with a polyatomic ion. So polyatomic ion. So even for polyatomic ion, I'm going to use the short form PAI. Okay. Now, so then in that case, all this settings are the ionic compounds. Ionic compounds. Now, keep that in mind that these ions will obviously have a charge. So metals will form a cation. This is a cation. Cations are the metals, and the anions are the non-metals and the polyatomic ions. Okay, so what happens here? So here is one example. The process of the solution formation is called solvation of ions. Solvation, and this is also called a hydration of ions. Hydration of ions. Okay, now solvation and the hydration of ions. How does this work? So here you have sodium chloride, for example, NaCl, and this is soluble in water. So first of all, this is a solid, and when you combine it with water, which is a liquid, this is giving you NaCl, and that is aqueous. Excuse me. Okay, that is aqueous. So what happens here? Keep that in mind, that it becomes aqueous. So this breaks up into sodium ion, aqueous, and chloride ions, which is also soluble in water, aqueous. So this aqueous is soluble in water. Soluble in water is aqueous, that symbol. Okay. Now, what's happening here is that water, look at this, water, hydrogen, oxygen, hydrogen, oxygen, and hydrogen, oxygen, hydrogen, oxygen, hydrogen, oxygen, hydrogen. Okay, so here we see that oxygen has the lone pairs. Every oxygen atom has a lone pair. Lone pair means these electrons are just sitting bunched up on one side. Hydrogens are deficit of electrons. So every oxygen will have a positive, every oxygen will have a negative charge, and every delta negative, very polar bond, more electronegative. Oxygen is more electronegative. So hydrogen will have a deficiency of electrons. So hydrogen will have a delta positive, and oxygen has a delta negative. Delta negative, delta positive. Delta negative, delta positive. Delta positive. Delta positive, delta positive, delta positive, and delta positive. And this guy is delta negative. Delta negative means a slight negative charge. So that is the bent molecule of water, bent molecule. So now when it's bent, then what does it do? It traps all the oxygen, surrounds these sodium ions, and sodium ions are positively charged. So you see they form this layer all around the sodium. Sodium being positively charged is now engulfed from all the three sides. Now, I'm only showing you two sides, but in reality, it's a sphere. It's like a ball. So every sodium gets surrounded by, every sodium ion gets surrounded by oxygen atoms of water. Then what happens? So basically it's separation of charges. Excuse me. Then what happens to the chloride? Opposite happens to the chloride. So chloride gets surrounded by the hydrogen, because hydrogen is positively charged. So it likes the negatively charged chloride ion. So I'm just drawing a little bit, just so lack of space. So here we have the oxygen with its lone pairs pointing away from the chlorine, But we see the positively charged or delta positive charge, hydrogens. Hydrogens are all delta positive. So each of these delta positively charged hydrogens are now engulfing. Engulfing means surrounding the chlorine, like a jacket, putting a jacket around chlorine. So what we see here is that the positive and negative repel. So that is why the negatively charged oxygens are, pointing in the opposite directions. And we see that positive are also going to repel. So positive and positive also repel, but negative and positive attract. So because of this attraction, we will see this whole process is called solvation or hydration of ions, because of which the ionic compounds this only happens in the ionic compounds that are soluble in water, not all of them. Ionic compounds that are, and we're going to look at the solubility in a minute, that are soluble in water. So if they do not dissolve in water, this is not going to happen. But if ionic compounds are soluble in water, then yeah, that's going to happen, okay? So this is one piece. Next is, let's look at the part B. This was A, B, C. Now we are going to look at the formation of solutions in the case of covalent compounds. Now remember that covalent compounds are formed by the covalent compounds. So covalent compounds are formed by the rule that is like dissolves like. So covalent compounds do not break up into ionize. Okay, so we will follow the rule like dissolves like. Now what does this mean? Like dissolves like. Like dissolves like is that the polar solutes are going to dissolve in polar solvents, and polar solvents, and then non-polar solute is going to dissolve in non-polar solvent. Okay, and then that is going to form the solution. All right. Now, the formation of a solution. In the case of covalent compounds, as we said, that covalent compounds will not ionize. Covalent compounds do not ionize. Do not ionize in, in water, mostly, in water and other solvents also, other solvents. So then what are we going to use then for the like dissolves like? So here in that case, we are going to look at the like dissolves like then applies to two things. One thing is that we look at the, the intermolecular forces. They come into play, intermolecular forces. Now, what are intermolecular forces? Intermolecular forces are, for example, intermolecular forces are, for example, dipole, dipole. We already discussed that in the previous chapters. So it's dipole and dipole, okay? So basically, then there is the London dispersion, and then there is hydrogen bonding, okay? hydrogen bonding. So let's look at this now. Okay, dipole dipole. Dipole dipole is, first of all, let's look at first is dipole dipole. So I highly encourage that you look at the previous video on intermolecular forces. We already covered that, but dipole dipole is when, for example, you have HCl. Okay, so here electronegativity plays a role. Okay, all of them. So electronegativity, sorry, let me just make it a little bit more. Electronegativity means that electron affinity, it relates to that, means love for electrons. And we know that the electronegativity, the trend in the periodic table. So trend in periodic table is that as you go from left to right, the electronegativity increases. So electronegativity is En and electron affinity is Ea. Okay, so electronegativity increasing. Okay, and electronegativity increases and electron affinity also increases. So when you move from left to right in the periodic table, going from left to right, okay? But when you move from top to bottom in the periodic table, top to bottom in the periodic table, we see that the electron affinity and the electronegativity, both of them go side by side. Electron affinity, it goes down. It goes down. Okay, it goes down. All right. Now we have this dipole dipole. We see that the hydrogen, for example, here, and chlorine. So chlorine is going to acquire, because chlorine is more electronegative. So chlorine acquires a delta negative charge. Hydrogen acquires a delta positive charge, right? And so because of that, this becomes a polar molecule. So polar molecule. And if you look at water now. Water. So here is your hydrogen. So oxygens, lone pairs, delta negative. Hydrogens, delta positive. This is delta positive. And we see the polarity is towards oxygen. The net polarity is towards oxygen. So water molecule is also polar. So anywhere you see, a more electronegative atom, everywhere you see a more electronegative atom, okay? So this is more electronegative. This is more electronegative. So there is going to be a polarity in the molecule. So always make sure you identify, and we already covered that in the previous chapters. So identify the polarity in a molecule. Polarity in a molecule. So if it is polar, it is going to dissolve in polar solvent. So polar and polar are going to mix. Okay, that's one piece. Next is the London dispersion. So that applies to the non-polar. So London dispersion. London dispersion is what? LDF. London dispersion forces, LDF. Okay, now what's happening here in London dispersion forces? So we see this is nothing but a spread of electron cloud. So spread of electron cloud. Okay, so in this case, this is going to apply to the, we talked about, so here is a non-polar and non-polar. So non-polar and non-polar are going to mix. So what are non-polar? So here non-polar solute, and the non-polar solvent are going to mix. So what we see here is that the non-polar solute and non-polar solvent. This means like for example, oil and grease, or let's say grease is a little bit. I mean, it doesn't matter. This can always change also. So grease and oil will mix together. Okay, different oils are. Okay, different oils are, a small amount of oil, like one type of oil in another type of oil. So the two oils are going to mix, right? So, this way, these guys, so you have to identify, if it is a non-polar. So generally keep this in mind that lots of carbon and hydrogen bonds make that site non-polar. Okay, so even though you have, like for example, in soap has one polar site, and it is made up of one non-polar site, one polar end. You can say it has got one polar end and one is a non-polar end. So what happens? The polar end mixes with polar end, gets attracted to water. So the polar end attracted to water, and the non-polar end, okay, let me remove this one. And the non-polar end is attracted to the non-polar, like oils. So this is attracted to oil, dirt, grease, okay? Because water is a polar end. Water is polar, and the oil, dirt, and grease are non-polar. So non-polar part is that chain, okay? So here is this soap. So I'll just show you here. So here, keep this in mind that CH2, 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 and so forth is also written as, this is the CH2, this is CH2, this is CH2, and this is CH2. Okay, this is another way of writing this. So keep this in mind that here is the non-polar end. Non-polar end is like that. It's a huge chain of carbon and hydrogen bonds. I bought a dog. I'll show you. He's a remarkable little thing. I rescued him from a shelter. He's just so cute. Okay, sit. Okay, sit. All right. Okay, anyway, so here we have this CH bond. Sorry about that. Okay, here is the CH bond, and on one side is this bond, CO. Let me just do it right properly. Okay, CO, O, and there's a negative charge here. Okay, so if you see this side is all this side, this is the non-polar end, but this side is the polar end. Why? Because you have oxygen with a charge. Okay, so what is soap? Soap is the soap, and you can look at the soap. The soap is the sodium salt of fatty acids. Those fatty acid is like palmitic acid, okay, fatty acids. So organic chemistry, and biochemistry, you will study these fatty acids, but Chem 30B, fatty acid is this. So this end is also called the hydrophobic end. So hydrophobic end is the end where you have, this is the hydrophobic, means it's afraid of water. So hydrophobic end. Hates water, but loves oil, oil, grease, dirt, those things. This end is the hydrophilic end. Hydrophilic end means loves. Hydrophilic end. And this means that it loves water, okay? And hates oil. So one end, so you should look at, so I'm going to just put a note here, that note, look at videos, on mechanism of action of soaps, especially how they make micelles, okay, and remove dirt and oil. So micelle formation. Okay, so that is the concept of London dispersion forces and the like dissolves like, basically non-polar and non-polar. When non-polar and non-polar, how they are attracted, and they do that. Okay, and the last comes is the hydrogen bonding. So hydrogen bonding is also hydrogen bonding. Okay, hydrogen bonding only occurs when hydrogen is attached to oxygen, and whatever is on the other side, it doesn't matter. When hydrogen is attached to nitrogen, and whatever else is, it can be 3 nitrogens, it could be 1 nitrogen, and it could be, it could be 3 hydrogens, it could be 2, it could be 3, it could be 2, it could be 1 hydrogens, okay? But we see here that the hydrogens is, like hydrogen is, and then also here, hydrogen and fluorine. So what do we see here? We see that hydrogen is delta positive. Why? Because hydrogen is attached to a more electronegative atom. Hydrogen is attached to oxygen, nitrogen, and fluorine. So hydrogen, oxygen, nitrogen, and fluorine. Only then hydrogen bonding is going to occur. If hydrogen is attached to anything else, then it won't. Okay. So here we see that in this case, for example, methanol or methyl alcohol. So here is this methyl alcohol, CH3OH. So how does this look? C, H, H, and H. And here you have O and H. Okay. Okay. So here's this oxygen and hydrogen. And now we have hydrogen is positive charge, oxygen negative charge. Hydrogen positive, and hydrogen positive. Okay. And sorry, wait a minute. Sorry, this because hydrogen is attached to carbon. So even though carbon is slightly electronegative than hydrogen, what we see here is that the carbon and hydrogen bond is still considered to be a non-polar site. So this site is the non-polar end. And this side, this is the polar bond. So this is the polar end. And in that polar end, there's the hydrogen. This hydrogen is the one that will takes part in hydrogen bonding. not the other hydrogens. So pay attention to that. This hydrogen takes part in hydrogen bonding. These three will not. Okay, so actually I should put that in a different color. So these are not available for hydrogen bonding. This, this, and this. Okay. All right. So how does this mix in water? So these guys, because of hydrogen bonding, they are going to mix. So even though the covalent bonds or covalent compounds will dissolve in water. Covalent compounds dissolve in water. Okay, so how does this happen? So here, look at this. So here is your hydrogen, carbon, hydrogen, and hydrogen. And here's this oxygen and hydrogen. And here is the, one second, oxygen, hydrogen, carbon, hydrogen, hydrogen, and hydrogen. Okay, so what is happening here? So I'm just showing two molecules. But if you look at it, this oxygen has a delta negative charge, and this hydrogen has a delta positive charge. This hydrogen has a delta positive charge, and this oxygen has a delta negative charge. These guys are not going to participate. Okay, these will just remain away. Okay, now what is happening? Here we see that this oxygen lends its lone pairs to this hydrogen. No, Nana, no, get down. Okay, this hydrogen and this oxygen going to be attracted. So it's a very weak electrostatic attraction. Very weak electrostatic attraction between. So this is always neighboring oxygens and hydrogen molecules. Oh, sorry, atoms. So you see that this hydrogen gets the lone pairs from the neighboring oxygen, and this hydrogen gets the lone pairs from the neighboring oxygen. So oxygens lend their lone pairs. Okay, so that is hydrogen bonding, HB, hydrogen bonding, HB. Okay, so this is hydrogen bonding. Okay, so lots of, so because of hydrogen bonding, and you can figure this out, identify the hydrogen bonding in a molecule and then, go from there. So identify hydrogen bonding in a molecule. First, do that. Okay. Identify the hydrogen bonding in a molecule, and then second, it will dissolve in water. Okay, then that site is attracted to water molecules, basically, is attracted to water. Okay, so in case, this is a very interesting, you have, let's say, octanol. Octanol is made up of 8 carbons, okay, and then 8 C8, H16, 15, O, H. Do I have this right? 1 second. So 1, 2, so 1, 2, 3, 4, 5, 6, 7, and 8. And then comes oxygen and hydrogen. Okay, and actually, like that. Yeah. So, so did we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. 18. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18. 18. Okay. All right. So this is what you have. Now this is called the octanol. So you see this top part, this part is the hydrophobic. Hydrophobic. Hydrophobic means that this is very greasy, oily end. Oily end. Okay, in octanol. But this part is more polar end. Greasy, oily end is the non-polar end. But when it's a polar end means that it is the like hydrophilic. Hydrophilic. And when we say it's hydrophilic, what does this mean? That means it is attracted to water. So if you have a test tube or something, you know, let us say this is a test tube or a container which is containing, you know, water. Okay. So here we see the water side is attracted. So the water, the OH actually dips inside the water. So OH, this side, not the oxygen, sorry. Here, this side is the hydrogen side inside the water molecules. So we see that this 2, 3, 4, 5, 6, 7, and then oxygen. And then here you have the hydrogen. Okay, the OH part also will go, sorry, I have to draw this. OH will also go. So the other part remains on the top. You see, so inside the water is, you know, oxygen here, hydrogen here of the water. So this oxygen and this water, this oxygen and this hydrogen are then attracted to each other. So this is the hydrogen bonding. This part right here is attracted to, let's do this here. Oh, sorry. Okay, so here is this hydrogen and this is hydrogen bond. Okay, so here we see octanol and you will see the oxygen of water and hydrogen like that. All right, so we see oxygens are negatively charged, or in other words, delta negative charge. Hydrogens are delta positive. Hydrogens is delta, each of the hydrogen is delta positive. Okay, hydrogen is delta positive. And then we have here hydrogen and oxygen attracted to each other. This oxygen and this hydrogen is attracted to each other. This oxygen and this hydrogen is already attracted to each other. So there is hydrogen bonding over here. This is the hydrogen bonding happening. Okay, inside. But the greasy or the oily end, hydrophobic end, is away from the water. Okay, polar end, hydrophilic, attracted to water. So due to hydrogen bond. Okay, so we covered this part, excuse me, like dissolves like. Now we are going to look at the electrolytes, strong, weak, and non-electrolyte, and the solubility rules. So strong, weak, and non-electrolytes. So next is, this is, which part was that? This is 3, this is 2, this is 1, this is part C, formation of the ionic compounds, general formation of a solution. Yeah, fourth part is, just put this here this way. Sorry about that. So this is 1. This is 2. This is 1. This is 2. This is 3. So we covered 3. And in that we covered, you know, 1 part, second part, and the third part, which was the light dissolved slide. Okay, now we are going to look at the electrolytes. After the electrolytes, we're going to look at the solubility rules. After that, we're going to look at the effects of temperature on the solutions. Okay, next is, and again, I'm sorry, there's too much noise outside, but if you would just focus on what we are doing here, and that would be just great. Okay. All right, now we are looking at the electrolytes. Now back to the ionic compounds, electrolytes. Electrolytes are those ionic compounds. So this applies to the ionic compounds, non-ionic compounds, or sorry, non-electrolyte. So ionic and covalent compounds, we will look at that. Ionic compounds, okay, yeah, ionic compounds, the ones that are soluble in water, and the ones that are not soluble in water, and then we are going to look at the covalent compounds. Okay, so let's first look at the ionic compounds. Ionic. By default, ionic means they ionize the ones, there are 2 types. One is that ionize 100% in water. Let me just bring this closer so you guys don't have the problem with the sound. Okay, ionic. So, first of all, let's look at what are the electrolytes. Electrolytes are like, if you take a container, okay, so here is, these are the, we are looking at the electrolytes. Okay, here you've taken this container, and in that container you put a solution. In that container you put a solution. In that solution you put the electrodes. Put the electrodes. Okay, now these electrodes are positive and negative charge. So this is called the cathode, which is the one that is positively charged, and the one that is negatively charged is called the anode. A-N-O-D-E, anode. Okay, now this is connected to a bulb. This is connected to a bulb, and this bulb is, the bulb lights up. Okay, that's what we are trying to see. Will the bulb light up or will the bulb not light up? If the bulb lights up brightly, the bulb lights up dimly, the bulb lights up, you know, like extremely, like quickly or slowly, or what's happening here? Okay, so now, and this is obviously connected to some kind of like, you know, electrical plug. So basically electrolytes are the ones in which the bulb lights up quickly and 100%. So bulb lights up quickly. Very bright light is given. Okay. So they are 100%, they ionize 100% in solution. Bulb lights up quickly, bright light, is seen. Bright light is seen immediately and 100% ionized in solution. For example, examples are like if you take like, let's say example HCl. HCl aqueous means HCl dissolved in water. This is going to give you hydrogen ions, aqueous, and chloride ions, aqueous. So 100% ionization in water, okay? Next is, for example, you have sodium hydroxide. Sodium hydroxide is aqueous, and this gives you Na plus aqueous, and OH ions are aqueous, okay? So 100% ionization, that's going to dissolve in water. Same is the case if you have a solution of potassium nitrate, but potassium nitrate aqueous, it is going to 100% break up into potassium ions, and it is going to give you nitrate ions, 100% ionization, 100% quickly, And for that matter, even H2SO4, although goes through the two-step process, but it will still, the bulb is still going to light up. So first it gives you hydrogen ions, aqueous, and then it gives you HSO4, 1 negative aqueous. Okay, then HSO4, 1 negative aqueous gives the hydrogen ions, aqueous, plus the sulfate ions, 2 negative charge aqueous. So, still it's 100% ionization. It's in two steps, 100% ionization. Whether it's in first one step or in two steps, it is still like these guys are still going to, the bulb will light up very, very brightly whenever you pass the electrical current, because electrical current is what? Flow of electrons. So the electrons are flowing, so bright light is seen. All right, so here you're going to put, like I said, this is where you're going to put these solutions. And then that happens. So this is one piece. This is electrolytes. Now let's look at the weak electrolytes. Weak electrolytes are weak electrolytes. So these electrolytes, basically, these are strong electrolytes. Strong electrolytes. Now we're going to look at the weak electrolytes. So what are weak electrolytes? Weak electrolytes are going to conduct electricity slowly. So we see that the bulb lights up slowly. Okay, so slow bulb, sometimes it takes very long. So bulb lights slowly, and we see a very dim light, and less than 100% ionization. Okay, less than 100% ionizing. IONIZING. Ionizing, okay? So here, here, and here. Now, what's happening here is that in what kind of examples? We will see the examples are for example, acetic acid. Acetic acid is vinegar. Acetic acid. Acetic acid is CH3COOH. It is a weak acid. And it, so when it breaks up, it gives you CH. And here you have COOH. Okay, now it breaks up into, the moment it breaks up, it goes back into its, molecular form. So this is the ionic form, C, H, and H. And here you have C, O, O negative plus hydrogen ions, right? And so, yes, this is the aqueous form, soluble in water temporarily, but it goes back, it forms this equilibrium. So pay attention to this. This is one line going 100% in one direction, but here it's going back. So it is a reverse reaction, and you will study this reverse reaction or a reverse, it's reversed, the reaction is reversed. So the moment the hydrogen ions are formed, they are not released, they are given back to the molecular state. Also, we see the other acid is the, this acid. So this was one example. Another example is HF. So this is the acetic acid. This is the hydrofluoric acid. Hydrofluoric acid AQ breaks up into hydrogen ion AQ plus fluoride ion AQ. Okay, but the moment that happens, because fluorine is very electronegative, it doesn't let the hydrogen go away. So it just quickly, it reverts back to that molecular state. And so it's just, it becomes so this is also soluble in water, AQ, okay? You see that. Next is the non-electrolytes. Non-electrolytes are strong, weak, and then the third is the non-electrolyte. So what are non-electrolytes? Non-electrolytes are, so this is the C. Okay, non-electrolytes are, they do not ionize in water. So bulb never lights up, never lights up. And so when that happens, what's the deal? So with the bulb never lights up because they do not ionize, in water or even in any solution. So what are the examples? For example, let us say like hexane. Okay, like hexane, let's do this. Or even like sugar, for example, let's do sugar. Like sugar is C6H12O6. So it is no ions. So in order to be an electrolyte, you have to have the ions, okay? So that's the thing. Let us see, yeah, or methanol, like sugar, or methanol, or methyl alcohol. This is also called methanol, 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 okay? And so this is CH3, and here you have OH. So again, no ions. Okay, so non-electrolytes are non-conductors of electricity. So non-conductor of electricity. Okay, and so these are good conductors of electricity. So where should I put this here? Good conductor of electricity. Okay, and these guys, weak conductors, are poor conductor of electricity. Okay. All right. Now we are going to look at the second last part, which is the solubility. Okay, so solubility rules. And then with that, we're going to look at the ionic, net ionic, and the solid 5. And here is the okay, solubility rules. Now let me get this information from the handout. Just give me 1 minute. Okay, so as you can see that in your handout on page 10 are the solubility rules. So this is in table 7.4 and table 9.7. So they're more or less the same, but I like to use the solubility rules that are related to the anions. It's easier. It's because there are less number of anions anyways. So here you have the general solubility of the ionic compounds. So as you can see that the group 1A, all of them are soluble, nitrates are soluble, acetates are soluble, all the chlorides are soluble. When ammonium attaches to anything, that makes it soluble. Now, there are some exceptions also. As you can see, the chlorides, I'm looking at this table, 7.4. As you can see, the chlorides are all of them are soluble except the silver and lead. Silver in +1 state and lead in +2 state. Sulfates, all of them are soluble except barium, strontium, and lead in +2 states. Then all the carbonates are insoluble except group 1A and ammonium. And similarly, all phosphates are insoluble except group 1A and ammonium. So let's write this down in the the ones that are soluble, let's write this down in your notes, and you can add more to it. So soluble and insoluble. Or maybe I'll put this on the, so soluble in water. So keep this in mind that something that is soluble in water, you will have AQ. Something that is solid in water would be insoluble in water. And so that is said as S. So that solid in water is S, and that is insoluble in water. Let me just put this separately. Let's put it here. Okay, so here, if something is soluble in water, then it is AQ. When something is insoluble in water, then it is S. And this is also as precipitate, P-R-E-C-I-P-I-T-A-T-E, precipitate. And we also write this as P-P-T. Okay. And then, of course, something that is a gas, is shown as that. And something that is a liquid is shown as this way. That's the states. Okay. So now let's look at the solubility as it relates to water. Solubility of ionic compounds, okay, in water. Okay, solubility of ionic compounds in water. Okay, so now we will look at this. Let's put it here, soluble. And then here, these are the exceptions. So let's do this. All chlorides are soluble. So where was that? 1 second. It's also given in your handout. So on page 10. All right, so we will see this now. All group 1A elements are soluble in water. Anytime ammonium attaches to something, it will be making it soluble in water. So no exceptions. No exceptions here. Anytime you have nitrates attached to any of the metals, nitrate, polyatomic ion, soluble in water, then you have acetate. Acetate is CH3COO, 1 negative. And the way they write it is C2H3O2, 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 1 negative. That is going to make it soluble in water. Okay, so that means there are no exceptions. Then you have anytime chlorides attaches to a metal, it will be soluble except silver chloride, AgCl, and lead chloride, and we are not doing mercury, PbCl2. It is going to be insoluble in water. So when we write this, so you can write this down, soluble would be AQ, and then the insoluble exceptions are the ones that is, so this is going to be like a solid. Lead chloride is going to be like a solid. Okay, next comes the sulfate. Sulfate is SO4, 2 negative. Okay, so this was 1 negative, 1 negative, 1 negative. So all group 1As are like lithium +1, sodium +1, potassium +1, cesium +1, you know, mostly, and rubidium, but generally these are common. All the sulfates are soluble in water except barium sulfate, BaSO4, like, so that is, then comes the calcium sulfate, and then comes the strontium sulfate. So these sulfates are insoluble in water. So you're going to write them as S. Okay. Then comes the next one are the ones that are insoluble. And then again, exceptions. So we have here insoluble, we have carbonates, CO3, 2 negative. CO3, 2 negative is insoluble, and the exceptions are the insoluble, the carbonates of this group 1A. So all the group 1A, when they combine, all the group 1A metals, when they combine with a carbonate, they are always going to be soluble. Or when ammonium mixes with the nitrate, then it is soluble. So when these group 1A elements are with the carbonates, they are aqueous, and ammonium is aqueous. Okay. Then look at the phosphates. PO4, PO4, 3 negative. All of them are insoluble except, again, group 1A and ammonium, and then, you know, those group 1A metals and the ammonium, all of them insoluble, will be soluble, sorry. And then also the hydroxides, this is missing. So hydroxides are insoluble except, again, group 1A and also ammonium, and also barium hydroxide is soluble partially. Okay, so when they are soluble, barium hydroxide, so we will write AQ. All right. And then there are sulfides, there are chlorates and other things, but these are the very general solubility of the ionic compounds. Okay. Now, the kind of questions that can be asked, we can give you some of these questions, like for example, identify the solubility. Excuse me. So solubility of the following molecules or following, following compounds. Compound is general term. So that's like on a test we will ask. So for example, if I give you barium nitrate, is it soluble or insoluble? Okay, so another way is also, let's do it this way. Identify the solubility of the following compounds and ionize them. And ionize them if soluble. And we are looking at solubility in water. Okay. Okay. Now let's look at this. So we talked about barium nitrate. So barium, if I say barium nitrate. So barium has +1, +2 charge, and nitrate has -1 charge. Now, how do you know? So first is, let's just put a thing here, which I hope you remember, that all group 1A, group number, and then the charges. Okay, group 1A has +1 charge. All the elements that are in group 1A +1 charge. Group 2A in the periodic table +2 charge. Group 3A in a periodic table +3 charge. Group 4A in the periodic table is +4, -4, and sharing of electrons. Okay, so that's a covalent. So that's what you get, 4A. Then comes the 5A, the charge is -3. 6A, the charge is -2. 7A, the charge is -1. And 8A, the charge is 0. Okay, and then also consult or refer to the to the table in handout. So this one, let's say 1 second. Let me put this here. Table 7.4 in handout. Okay, and then the other piece is this piece right here, was the table of more than one positive charges, and that table is table 6.5, page 5. Okay, table 6.5, page 5. Okay, so here, what is that table? This is the table on metals with more than one positive charge. So metals with more than one type of positive charge. Like, for example, copper can go to copper +1 and +2 state. Iron can go to +2 and +3 state, right? And then tin can go to +2, and tin can also have +4 state. Okay, so that's the these things. So these are the very important pieces here. This is one piece, and this is also in your table, and then the second is this table. Okay, so here, so now we see that this number comes here and this number comes here. So basically it is a review nomenclature. Here, review nomenclature, writing the names and the formulas. And in the nomenclature, very specifically formulas, you know how to write the formula. That is important. So that's something you have to, again, consult the handout or look at the books, and also the lecture notes. So here, when you crisscross, what do you get? You get BaNO3 whole twice. All right, BaNO3 whole twice. That's one piece. And so this is the nitrates. All nitrates are soluble in water. All nitrates are soluble in water. And so when they're soluble in water, this is aqueous. Okay, so this is one piece. Second is, let's say, calcium hydroxide. So you see calcium is present in group 2A, +2 charge. Hydroxide, OH ion, -1 charge. So I cannot, so this is a very important piece right here. You can't just, ignore this. So just make sure that, you have this. Okay, review the nomenclature, writing formulas. Okay, now calcium hydroxide. So you have calcium. So here you have this 2 comes here, and then this 1 comes here. So this becomes CaOH and whole twice, calcium hydroxide. Next is you have 1, 2, 3. Next is you have, let us say, tin 4 phosphate. Oh, I forgot here. So this one right here, we are doing this calcium hydroxide. So all hydroxides are insoluble. And calcium is not an exception. So you need to start looking at the tables. It's not following in the exception. Okay. So this one is, so you have to refer to that table. And okay, is not an exception because calcium is not present in group, calcium is a group 2A. Calcium is not group 1A. So calcium is in group 2A. Okay, next is, oh, tin. Sorry about that. This is SN, that is tin. Tin 4A phosphate. I'm a little bit distracted here. So this calcium hydroxide is solid. Okay, all hydroxides are insoluble. Sorry about that. Okay, so now we have this tin 4 phosphate. So tin 4 phosphate is tin. Tin is SN. 4 means plus 4. Phosphate is PO4, 3 negative. Okay, so you see this number comes here and this number is going to come here. So what do you get here? You get SN 3 PO4 whole 4. All right, and so what does this become? This is tin 4 phosphate is this is phosphate. So all phosphates are insoluble, so solid. And this is tin is not an, SN is not an exception, which means that the not group 1A. So that is the exception. So tin is not group 1A. Therefore, not exception, not an exception. So that is why it is going to be insoluble. Okay. And so next is, let's look at a few more. 2, 3. So here we have, let us say, so we got the nitrate, we got the hydroxide, we got the phosphate, carbonate, Na2CO3, and that is, sodium carbonate. And sodium carbonate is, sodium is Na and carbonate is CO3. So -2 + 1, group 1A, sodium, and carbonate is -2. So what is happening here? We see that this 1 comes here and this 2 comes here. So the formula becomes Na2CO3. And Na2CO3 is group 1A, sodium is in sodium. sodium is in group 1A. So when it's in group 1A, that means it is soluble in water. And when it's soluble in water, that means it is going to have AQ written here. Okay. Then let's do one more. 1, 2, 3, 4. And then let's do one more. And that is ammonium sulfate. So ammonium sulfate is NH4. Let's put this here, red color. +1 charge, sulfate, SO4, -2 charge. And so what happens here is this comes here and this comes here. Okay. And so what do you get here? This is NH4 whole twice SO4. Okay. Ammonium sulfate. Ammonium sulfate is soluble in water. Why? It is aqueous because it is ammoniums. Ammoniums are NH4s. All NH4s soluble in water, always. Okay, so we covered quite a bit of this, the rest is just practice. So just make sure that, you understand the solubility of ionic compounds, which is based on these solubility rules, okay? And then, I learned to ionize them, because now we are looking at the next part, which is the molecular equation. So here, let's do this thing here. This would be solubility 6. Or wait 1 second. Based on the solubility rules, this is part A. Let's do the ionizing equations. This is ionizing equations. Okay, ionizing equations. And you see here, when you ionize, what happens? Ionizing equations. So first is the molecular equation. Molecular. So in other words, let's do this way. First is identify. So this will be a review also. Identify the products. Second is balance the equation. So that balanced equation is the molecular equation. Okay, then comes the balancing, then comes the solubility. Identify whether something is soluble, would be aqueous, insoluble is S, whether something is liquid, whether something is gas, based on all that. Then you ionize it, ionize. So this is, ionize means total ionic equations, total ionic equation. Then identify the spectator ions. Spectator ions do not show change in phase. Means they will remain aqueous on all the two sides, reactants and the product side. Okay, change in phase on reactant and product side. Okay, then comes the net ionic. So what is a net ionic? Net ionic is those ions that show change of state. So those are shown there. Those ions that show change of state. Change of state. All right, let's do this now. Let's bring in one problem from your book. And I'm going to cover the equivalents later on, but let's see. Okay, so you have predict whether a solid might be in each of the following mixtures of the solution. Ammonium lead nitrate and KCl. Let's do that. Study check 9.5. So here is the number one. Study check. (9.5), page 339. Page 339, and this is part B. And here you are given this solution of lead nitrate. So lead nitrate is reacting NO3 whole twice, and this is aqueous. All nitrates are soluble in water. Reacting with KCl. KCl is also aqueous, which is again soluble in water. So right now I'm removing this because it takes a lot of, so identify the products, what are formed. Okay, so here, remember that outer, outer, inner, inner. So we covered that in one of our previous lectures also. So this is the outer atoms are going to combine, outer are going to combine, okay, and inner. And you have this nitrate, and potassium. Nitrate and potassium are going to combine. So you are going to get Pb with chlorine. And so remember that Pb is in +2 state. This 2 is coming from the top of lead. So like I already covered that. This 2 is coming from the top of sulfate. Remember that. So for 1, we never write. Remember this 2 is coming from the top of carbonate. Remember that. This 3 is coming from the top of phosphate. And this 4 is coming from the top of tin. Similarly here, this 2 is coming from here. So you see this is crisscrossing. So you need to really master that. Okay, so that's how you will get that. And 2 is coming from the top of lead. So here this becomes PbCl2. That means lead is always going to be in +2 state. And you are given, the next one is always metal is written first, and then comes the polyatomic ion or the non-metals. So we have PbCl2 and lead nitrate. So what do we see here? Here we see, first of all, then first is identify. So you identify the products. So here, identify the products. Okay, so always metal written first. Metal is written first. All right. Okay, so this is one piece. Next is balancing. Balance. So okay, so we have Pb NO3 whole twice reacting with potassium chloride. This is giving you PbCl2, PbCl2 plus potassium nitrate, KNO3. Okay, so now look at the lead is 1, nitrates are 2. So when you're balancing, okay to not put charges, because sometimes for the students it's too confusing. Some students, not all the time, but it's okay to not put charges while you're balancing. So lead nitrate is, how many nitrates there is? There are 2 nitrates. Remember that this 2 applies to all of this nitrate. This 2 applies to only chlorine. Okay, and this is this whole big nitrate. NO3 is one thing. So it's very important you recognize the polyatomic ions. Okay, next is, we're going to look at, next is potassium. Potassium is 1 and we have chlorine 1. Okay, here we have lead 1 and we have chlorines 2. We have potassium 1 and we have nitrate only 1. 1:1. Okay. So what is not balanced? So we see that the nitrate is 2 and here nitrate is 1. So that's not balanced. We say chlorine is 2 here. We have chlorine 1 here, not balanced. So what will you do? You're going to change this and make it the nitrate to be 2. 2. So when you do that, this 2 applies to potassium, this applies to nitrate. So this becomes 2 potassiums and this becomes 2 nitrates. So nitrate and nitrate got balanced, but something else got tipped, that is potassium. So we need to make the potassiums 2 here. So we are going to, this 2 applies to potassium and chlorine. So now we have 2 chlorines and we have 2 potassiums. So potassium and potassium got balanced. Chlorine is 2 here, chlorine is 2 here, balanced. Lead is 1 here and lead is 1 here, balanced. Okay, so first balance the equation. Next is you are going to do 3. You are going to next identify the solubility. So now solubility, we are going to put here PB, all nitrates are soluble in water. So therefore this is AQ. Next is all chlorides are soluble in water. And we have here 2 KCl, potassium is group 1A, soluble in water. This is giving you PbCl2. All chlorides are soluble in water except, so this one is an exception, lead PbCl2. So this is going to be a solid. So always refer to the table 7.4 in handout. Okay. All right. Next is the potassium nitrate. So 2 potassium nitrate is, nitrates are soluble in water, aqueous. Okay. Nitrates are soluble in water, aqueous. Now we have here, we identified the solubility. Next thing is ionize. So when we ionic, so here is the total ionic equation, total ionic equation. Now total ionic equation is an important thing. Do not ionize the precipitates, and those precipitates are solids or the insoluble compounds. Okay, so if they are insoluble, that means they will not ionize. Okay, that is why they are insoluble. So now we are going to ionize. So basically, it looks like it's a lot, but really once you do the balancing, now here it becomes easy. Now you can start putting the charges. Sorry about that. Okay. Now you can put charges. Okay, so here we have, let me write this down, Pb, NO3 twice, aqueous plus KCl 2 aqueous. This gives you PbCl2 solid plus 2 KNO3 aqueous. So now we see here Pb plus 2 charge aqueous. Remember that this 2 is coming from the top of lead. Remember that this 2 is coming from the top of lead. Okay. All right. Next is nitrate. So there are 2 nitrates. Nitrate always have -1 charge, aqueous. Then you have 2 potassiums plus 1 charge aqueous, plus 2 chlorides plus 1 charge aqueous. Okay, remember that this 2 applies to potassium and this 2 applies to chlorine. This 2 only applies to chlorine. This 2 only applies to nitrogen. This 2 applies to potassium and nitrate. Okay, so always recognize the polyatomic charge ions. Okay, anyways, PbCl2 is a solid, so it is not going to ionize. So remain as it is. Plus 2 potassium ions aqueous, plus 2 nitrate ions aqueous. All right. Now, once you do that, this is your total ionic equation. Okay. Then you are going to see what are the spectator ions. So here, the spectator ions are the ones that do not show the change of phase. So do not show phase change. So which ones are those? So we see that here the nitrates is aqueous. 2 nitrates are aqueous and 2 nitrates are aqueous on this side, on both the sides. You see that? And then you also see 2 potassiums are aqueous on one side and 2 potassiums are aqueous on the other side. So the spectator ions are the ones that are in green. So we have here the 2 nitrates, NO3 with -1 charge, aqueous, and you have 2 potassiums plus 1 charge, aqueous. Okay, and then you have, next is the net ionic. Now net ionic is where the elements that show the change of state. So the ions that show change of phase. Okay, so which ones are those? So here we see lead, Pb +2 state going from the aqueous state, actually combining with 2 chloride ions, 1 negative, aqueous state. They are giving you PbCl2, and PbCl2 is a solid. Okay, so we see that this is the net ionic equation. All right, guys. So, you know, you will have practice. There is a worksheet on, you know, ionic and net ionic equations. Okay, so those you have to do, you know, and upload, you know, so that's a worksheet assignment. So it's a proper assignment. And it's graded. All right, now comes the last part in our lecture today. It's been a very long lecture. Next is the effects of temperature and pressure. So that's the, sorry about that. That is the 6th part. Sixth, effects of temperature and pressure on solubility. Okay, so keep this in mind that temperature, first of all. Temperature. Now, temperature with regards to solids, when the solid solute. So when the temperature increases, this is, you've seen that, hot coffee versus cold coffee. Hot coffee, easy to dissolve the sugar. Cold coffee, difficult to dissolve the sugar. It takes longer. You have to stir more, right? So as the temperature increases, the solubility of the solid increases. Okay, but if the if it is a gas solute, like for example, let me put examples also here. So here is the gas solute. So as you, solid is, for example, sugar plus hot coffee. You know, little bit of stirring and it dissolves. So this is what it means. You're cooking food, right? You're cooking soup. You know, you want to mix certain things. If you heat it, it will dissolve faster. So temperature increases, the solubility increases. But here, if you have carbon dioxide in the hot water, will not mix. In the hot water, does not mix. But if you have a carbon dioxide, this is a gas. Carbon dioxide is a gas. And this is mixing with hot water as a liquid. And here you mix it with cold water. It mixes. So for the gases, when the, for the gases, if gas is a solute, when the temperature is gone down, means cold, then the solubility increases. So keep that in mind, that it's opposite. Solids, liquids, it doesn't matter. You know, I mean, obviously a little bit hot is still going to matter. But if the solids, temperature increases, solubility increases. But for gas, if the temperature increases, it does not mix. When it's cold, then it mixes. So that's one piece. Next thing is about the pressure. And that is Henry's law. Okay, so that is Henry's law. And so what is that? That applies to the gases, only when for the gases as a solute. So here we see the gas, when the pressure here, when the pressure increases, then the solubility of gases also increase. Okay, solubility of the gases also increase. And when pressure goes down, then the solubility also goes down. And this is the reason why the one example here is, that the Coke tastes bland at room temperature. Why? Because all CO2 becomes depressurized, you know, becomes like it's not under pressure anymore, becomes depressurized and escapes. Okay, it escapes. So that is why it tastes bland. But Coke tastes like fizzy on the tongue, you know, or in the mouth, fizzy in the mouth. Why? Because of CO2 soluble in cold Coke. Okay, so that finishes this part, and we will have the other remaining part, which is the milli-equivalents, and then there's the other concentrations. I'm going to cover that in our next video. So that is, you know, my notes here. I'm seeing that the students are, you know, some of the students are actually making printouts of my notes, which is a great thing, but just don't sell them. That's the thing, you know, because I looked at some of the pictures, you know, some students printed it out and it looked really nice. So, you know, it's all my hard work. So anyways, so here is the my notes from, and this today is 25. Okay. All right. So I'm going to stop recording now. If you guys have any questions, please feel free to ask, and you can always, put your information also in these, in these notes. So feel free to use them as you like, but just don't sell them. That's the only thing. Okay. All right. Thank you for watching. Bye-bye.